There we go. All right, so I am very excited about today because today is where we kind of go from making these cool applications that live on our computer, and that's just all they do is they do fun things on our machine. And we're going to be starting to move towards things that can actually interact with the wider world, because we're going to be talking about the internet. And specifically right now, we're going to be talking about HTTP. So can I present this? Yes, I can. There we go. So HTTP, I heard somebody mention it earlier. What does that stand for? Hypertext Transfer Protocol. So this protocol is the protocol that makes the internet possible. So yeah, Hypertext Transfer Protocol. It was originally described in 1999 with the origins of hypertext itself dating back as early as 1930. So we talk about hypertext. Hypertext protocol was originally designed as a protocol for transmitting hypertext. The modern equivalent of hypertext is HTML. Like, understanding what hypertext is as important as understanding HTTP. So today, HTML has grown to support more than just linking from one page to another, but that was the concept of link pages that uniquely defined the early web. So people know kind of the origins of the internet. It started out at CERN, I believe. It's just a way for researchers to share data, and then eventually grew into the World Wide Web as we know it. So HTTP was originally for just transmitting hypertext and then HTML, but it can transfer any type of document or file. So the most common documents transmitted over HTTP isn't even HTML anymore. Got images, CSS, JavaScript, API responses. They're way more common in the grander scheme of things. But it also happens every time you go to a new website, is an HTTP request happens. So talking about the internet, who here has seen Wreck-It Ralph 2? Ralph Breaks the Internet? It should have been called Ralph Wrecks the Internet, and that's a major missed opportunity on their part. But the reason I bring that up is in that movie, you know, the main characters are video game characters who go into the internet and go around. They go to eBay, they go to Amazon, and they go to about like these websites are like physical places that they can visit. But that's not really how the internet works. The internet is a conversation. And it's a conversation between many pairs that consist of two parties. Those consist of a client and they consist of a server. So in this conversation, are we the client or are we the server usually?
Usually it depends where we're at.
Yeah, it depends on where we're at, but in our day-to-day lives, we're usually running the client. And that client can be your internet browser, for example. And that's usually what it'll be. It'll also be many programs that you write over the course of the next couple weeks. So we are the people saying, hey, I want to go to a website. I want to see this. I want to see some data. The server is a computer that lives on the other side of this conversation and will either give us that information that we want or won't, depending on how we ask. So the whole conversation consists of requests and responses. As the client, we make requests. As a server, we make a response. So both the request and response are plain text. They're easily read by a human, and each one has a very simple structure. So if we take a look at that, so here are examples of a request and a response. So we're going to go into both of these in more detail. So the first thing it has is the request line, which is broken up into three parts: the method, the URI, and the protocol version. So the protocol version is just, hey, we're making an HTTP request using Hypertext Transfer Protocol. The URI is kind of where we're looking for, and the method is how we're actually asking. Has anyone heard of like a GET request before in any kind of context? Yes, what is that?
You're making a request from the server for some kind of information or something like that.
Yeah, so we're making a request to the server to get something. We're trying to get information from the server. So there are many different kinds of HTTP verbs, but there are 4 that are the most common. So GET requests, whenever you visit a website, we're making a GET request, just saying, I would like to see this resource. Whether that's visiting a web page or making a JSON API call, that's a GET request. A POST request is setting up a resource. So in real life, what's an example of a POST request that we make every day?
Password login.
So logging into a website. So in that case, we're sending a resource up. Yeah, that would count as a POST request. Any other examples?
Noah, if we do the daily check-in forms, is that considered a post request?
Absolutely, it is.
Yep.
Yes, very good example. The daily check-in forms. So you fill out a form, hit the submit button, and you've created a resource that we can see. Send into a big Google spreadsheet in this case. But even something like posting on Facebook or making a tweet, those are all post requests. A put request is updating a resource. Sometimes you also see it called a patch request. There is a difference between put and patch. It's a small difference, so just don't worry about it. If you see put or patch, that usually just means you're updating something. So editing your an existing Facebook profile, editing an answer at any point like that where you're changing something that already exists. And delete. Pretty straightforward. So you're going to be working with all of these HTTP verbs from now on. So just kind of get used to seeing them. Get, post, put, and delete. You probably won't have to deal with the other HTTP verbs, but they are out there. So be advised. The URI stands for Uniform Resource Identifier. So you notice it's going to /bio.html, but it doesn't say the name of the actual website, right? So we're kind of talking a little bit about how URLs in general are formatted. So in our request, we have our URI here, and we have the host here. So example.com, if we add that to the URI, we have example.com/bio.html, which stands for URN. And then if we add the protocol into the back of that, we get a URL, http://example.com/bio.html. So I'm going to get out of this real quick. So if we kind of look at this, we have http://docs.google.com. So in this case, our host is docs.google.com. And then our URI is this whole thing. So a lot of information can be in the URI. In this case, because this is just a big unique identifier that also includes things like saying how we want to be presenting this. But we can also take a look here. http iruntheinternet.com lulsdump/images/gifs/the IT crowd gen presents the internet box. So these are all examples of URLs, and just remember, so without this, it's just a URN, which can still work the same way, and then everything after iruntheinternet.com is the URI. All right, so before we move on, just any questions about what we've talked about? What questions do you have about what's happened so far? Talking about, verbs and URNs and stuff like that.
User agent, that's just who's accessing it, right?
Yes. Okay. So the user agent is information we give about who's accessing it, so often you'll be accessing it through a browser.
How does HTTPS differ from HTTP?
Good question. So you may have seen HTTPS on certain things. HTTPS is a newer protocol. I believe the S stands for secure. So HTTPS requests have a added layer of data security onto it that supposedly make requests safer, so you're less likely to get people hijacking things and things like that. I don't know how it works exactly.
I think it's just encrypted. Yeah, it's encrypted.
Yeah, it's encrypted.
It's a different form.
Yep. So most websites now, if they really have any kind of security on them, will automatically be HTTPS. I know you have to, in order to do that, you need to like pay for a certification to show that you are actually HTTPS. You can't just say my website uses HTTPS if you aren't encrypting anything.
Self-SSL is free, but it's not verified by a third party.
Yeah, it's free but not verified by a third party. Yeah. All right, so that first part with the verb, the URI, and the protocol is the request line. After that, we get the headers. So the headers is a place for us to include more information. So the host is necessary, the user agent is necessary. There are other things that may be included in the headers as well. Then after that, you get a blank line, and then the body, which is always optional. So the body includes any kind of information you actually want to send to the server. So the example they use here is a query, like if you're searching for something. So this is actually a post request to /search. And we look at the headers. The host is example.com. The user agent is Google Chrome. The content type is something we can include in the headers, saying what we want to get. And then the request, they're most commonly put with post, put, patch, and delete requests, but they can also include all types of content. So in this case, we're saying we're adding in the extra information that we're looking for new Jordans that are red. So additional request data can be included as part of the URI instead of being included in the request body. So they did search $query equals error Jordans color red. And so you can do that instead of being in part one of the in the body. Query params are separated from the URI with a question mark, and individual query params are separated by a ampersand. Query params can be combined in the request bodies. So if you want to take a look at kind of this in action, go to Amazon.com. And if I was to type in, I don't know, steel cube. So we can see here, they didn't use query, but they have search question mark K equals steel plus cube. And then they have and ref equals something called NBSB NOS2. I'm not sure what that's about. And I have everything I need for my steel cube needs. But I could also just, type in something up here. So like, parasol. So I just included that. So when I made my GET request to this search thing, I essentially used Amazon's search bar without actually typing anything in there. I just used it, put it in the URI directly. Oh, these are all very pretty. So headers provide additional context. So the examples that we've been using, the host tells the web server which domain the client is requesting information from. Often a single web server will serve content for multiple domains, sometimes called virtual hosts. The server uses this header to determine which content to serve. We can do things like what languages we'll accept. So accept language English, saying, hey, we're looking for something that is only in English. Again, user agent, Google Chrome, what type of client sent this request. The server is able to make decisions on whether or not to give it to you, depending on what it is. So if you wanted to ping a resource from the command line and the server was set up not to do anything that wasn't from a browser, it could deny your request on those grounds, for example. And then we can talk about what response that we're interested in. So we can ask for text or HTML, we can ask for plain text, we can ask for an image or JSON, any of those. So before I move on to responses, what questions do you have about requests?
So the browser asks for the type to be returned.
Mm-hmm.
What if the browser doesn't know the type?
When you say if the browser doesn't know the type, do you mean the client or the server in this case?
The client does not know what to ask for. Is that accept optional or not?
Yes, so the accept is optional. Most request headers are, except for the host. If you don't, I don't want to make assumptions on what happens if you don't include an accept here. Usually, in most contexts, that'll kind of be formatted for you. Like, we want you to understand what these requests look like. You won't be writing them out in plain text yourself, I don't think, because there's software that does that for us. And we're going to be talking about one of those after the break. But yes, so most of these are optional. I think if you don't include an accept, your response will just be whatever the server decides to give you. So you don't have, it takes away your option to say, hey, I want HTML, not JSON, for example. And sometimes a server will say, I can't give you what you're going to accept, so it's going to give an error. Good question. What other questions about requests do you have?
Is the client able to say that it's something that it's not? The reason why I asked this, so sometimes I hate mobile websites because they always give you a dumbed down version, and I often find I can't do something that I want to do that the main version has. And I thought that the, show me the normal full-size option fixes that, but with interactive websites, they say, no, you're on a mobile, this is what you want. Is my device able to say, no, I am on a desktop?
So Ian in the chat mentioned that you can fix the user agent. Ian, do you want to expand on that a bit? Uh-oh, I can't hear him.
Oh, sorry. So you can, in fact, fake the user agent. So I developed a web scraper back around December timeframe because I was trying to buy a hot selling item. It was the AMD Ryzen 9 or 3950. So all these websites would, they'd have it in stock for 5 to 10 minutes, and then by the time I got the notification, it would it'd be sold out. But so I believe it was Beautiful Soup 4 that I used, but you can actually specify what user agent you can use. I think I had a list of user agents, and it would just like randomly select one. So that way it didn't seem like I was a bot. Anyways, I did end up getting that Ryzen 3950. So
Good.
Just to touch up on that, I've had some experience with that too. Yes, you can fake it, but also the server can actually give tests to a browser, and different browsers will solve different tests differently. And the server can actually detect what browser you're using by giving you different data and seeing how you respond.
Yep. So you can fake it, but also a server, if it's looking for that, can usually detect if you are faking it. Yes.
I'm pretty sure Chrome on mobile devices has an option to go in and be like view as desktop site.
They
for a
do,
lot
but
of
then it
times.
doesn't work.
Oh, really?
Yeah, because they're learning how to get around that.
It could also read the CSS looking at the device. Doesn't necessarily know that it's a mobile. Could be looking at the desktop, the CSS and media queries, and determine, hey, this is
The size.
Yeah.
It's based on the screen size.
Right. I figured you could spoof that too, right? Just claim that you're larger than you are.
Because it's percentage based
Yeah.
usually. It's
Yeah.
not
Yeah.
actually
knows
like
the size of
hard
the
numbers.
numbers of the screen.
It couldn't lie, tell it I'm bigger than I am.
I mean, I don't know if there might be some JavaScript in that, but I don't know.
Gotcha.
So we're talking about how sometimes even if your browser, your like mobile phone browser, is telling the server that you're not on a mobile browser, sometimes the CSS is automatically formatted to fit your screen, regardless of whether it knows that you are in a mobile browser or not, because it's often percentage based. So it'll just, warped fit a mobile screen because that's what it's designed to do. It doesn't care about what kind of HTTP request happened. Let's talk a little bit about responses. So this is an HTTP response. So it starts with a status line, and then like the request, it has headers, a blank line, and then a body. And that body can include, in this case, for example, it can include an entire HTML document, but it can include many things. So that response status line consists of 3 parts. Again, the HTTP version. But we also have a reason phrase and a status code. So status code 200 means that everything is fine. Status codes are how the internet uses to tell how a response went. There are many, many status codes. Some of the most common, if you get a 200, it means everything worked. So a 200 is what we're looking for in most cases. A 302, so anything, and it's all organized by first digit, so anything starting with a 2 usually means it's a success. If it starts with a 3, it's usually has something to do with being redirected. So a 302 is see other, aka redirect. If it starts with a 4, it means that something you, the client, did was wrong. So error 400 is a bad request. Error 401 is unauthorized. Error 404 is you're looking for something that doesn't exist. So if you see any of these error 400s, it means that you as the client screwed up somehow. And if it starts with a 5, it means something's going wrong on the server end. So if you see an error 500, it means something's going wrong with the internal server error. And when we're setting up a server, we want to not get an error 500 if at all possible. And if you ever want to look it up, there are dozens of these status codes. Some of them are actually jokes. I think error 4, I want to say 426 or something, is called "I'm a little teapot." I may be wrong in the exact number, but it does exist.
So there is like a 402 and a 403?
Yep. Yeah, these are just, again, these are the ones you're going to encounter most often on the internet.
Isn't it a bad practice from a security standpoint for the server to admit error 401? Because then the server would admit that, hey, you found something that you can't view, as opposed to the server just returning 400 error.
Good question.
I think 401, you want to be as transparent as possible to the user.
Yeah.
But you'll see there's different. You'll see a lot of things that are unauthorized come back as 200s. It's like, all right, you reached it and you got a response back.
Yep. Yeah.
Okay,
but
that's what I was wondering.
Yeah. So what Pavel was asking is giving an error 401 a security threat because you are telling the person who does that you aren't authorized to see this, but it's there. And we were saying that it's not really a security threat. It's important to be as transparent as possible. But for example, sometimes you'll visit a GitHub page when you're not logged in, or it's a repo that you don't have access to, and they give you an error 404 there instead of an error 401. I'm not entirely sure their rationale behind that, but that is their practice.
And when you're writing code and you're debugging, well, I guess that's not really relevant. You should have access to disregard.
All right, so again, headers are a similar response to the request headers. They give you additional context that the client can use to interpret it. So you'll usually get a content type saying what format is this body so that the client can use that to properly parse the response. So whenever you visit a website, it's going to say content type text HTML. Your browser takes that HTML and any CSS and JavaScript that also gets sent over and literally builds the website on your screen. That's what the browser does. It also has to include the content length, so how many bytes long is it? They have things about setting current cookies. So this header requests that the name save a cookie with a particular name and value. And they also include the date when the response was sent. So an HTTP request is actually often consists of many requests. Dozens or hundreds of HTTP conversations will take place. So when I said your browser literally builds the website from the response, so it can only send a couple one piece of data at a time. So you'll get loading a home page gets you the HTML. You make the request to the server, it gives you responsive HTML. Then it makes another request for the CSS file, another request for the JavaScript file, and another request per image on the page. So that's just one single page. So that's why you'll sometimes find if your browser is your connection is really slow, websites with a lot of images will load the slowest, and it's always the images that load last. That's because your browser has to make these requests back and forth for each image that it has to load. And images tend to be very large files, so those files take longer and your connection is bad. So a very important characteristic of HTTP is that every conversation shares no state with any previous conversation. HTTP is always stateless. Every conversation begins with a new connection from the client to the server, and it's as if both parties are meeting for the very first time. even if the requests are made one after the other, they have no bearing on the current request. So HTTP can't save data like between requests. So most servers clear all state variables with each request. That means all state when processing a request comes from the request itself. So it's stateless, but you'll probably notice that when you log into a website, you'll tend to stay logged in, right? And if you set preferences on a website, you generally tend to keep them. The question is, how can this be if HTTP is stateless? TCP/IP? Could you expand on that?
There's another protocol that lets you connect and confirm that there's a connection between your server and client that you're communicating, and that's an authorized connection.
Yeah, so there are other types of protocols, including TCP/IP, but that doesn't help us save the state of like our Facebook page staying logged in after we close the browser.
So cookies.
Yeah, cookies or browser data. So HTTP cookies help retain state like who was logged in and what was their last search across multiple results. So when you have cookies on your browser, it's saving information on the client side, so that next time you make this response request, you can check and it'll check and say, okay, here's what's happening. I've saved this data. So it may sound like a total violation of the stateless nature of HTTP, but even with the cookies, the protocol itself remains stateless. It just has to do with how the cookies are implemented. So we're going to talk more about how the cookies work later, but here's a summary. The server sets cookies by sending them to the client as part of the HTTP response. Then the client stores the cookies, not the server. Any cookies for the current domain are sent to the server as part of your request. So talking about, if you're logged into a website, when you log in, the server will send back some kind of token saying, okay, this is your unique token saying that you are logged in. The browser saves that, and then every time you request that, make a GET request to the server again for this website, along with everything else, it'll send up this token that it's saving saying, hey, I'm already logged in. Here's my password, essentially. Here's my token. So it's not your password. It's a unique, randomly generated token. And that's why when you clear your cookies, you get logged out of everything because it doesn't have that token. You can't send that token up to the server anymore. It just sends up saying, hey, give me a basic request. All right. What questions are there about responses and cookies and HTTP requests?
Do we know why they were called cookies?
That's a great question.
That is a very good question.
Because they leave crumbs.
Maybe because they leave crumbs. You know what? I've never actually looked that up, funnily enough. Let's do that. Why are cookies called cookies? Well, that's not exactly right, is it?
HTTP, I think. So look up HTTP.
All right. Take a look, origin of the name. The term cookie was coined by web browser programmer Lou Montulli. It was derived from the term magic cookie, which is a packet of data a program receives and sends back unchanged, used by Unix programmers. So we have to, why that's called magic cookie. So it's a token of short package. Doesn't really say why it's called that.
Wikipedia deep dive.
If you go back, they kind of started to talk about how you came up with the...
You're right. So, honestly, it was probably just somebody decided to be cute. It was like, yeah, it's like, what do we call this packet of data that we send up when we make a request? It's magic cookie. Why not?
I mean, if you think of like baking, taking different ingredients together. It's like,
That blue is real restful, I'll tell you.
Yeah, it's always fun learning about like how certain things that we take for granted now became a thing, like why the computer bugs are called bugs, for example.
Right?
Yeah.
They ruin your
There's actual bugs.
Yeah, no, like, it's kind of an apocryphal story that Grace Hopper solved a computer issue by finding a moth that had thrown into the computer, took it out, and that was the first computer bug. Any other questions about cookies or how this like kind of request response cycle works? Okay, so it's a proven protocol. It's extensible. It's been used, has found uses far beyond what was imagined when it was first implemented in 1991. It's relatively simple. It's human readable and easy to parse with code. It first changed the world by connecting users and servers to form the web, but today it's the foundation of so much more than the web. You'll soon realize that HTTP is everywhere. All right, so the main takeaways here, if there's nothing else you remember, is just understand that when your browser or you as the client, however you're doing it, you ask a question of the server saying, can I have this, or can I post this, or edit this, or delete this? And the server will either tell you yes or no, and give you any other info. And if it allows you to get the information, they'll send back the information. And that's how the internet works. It's just millions and billions of conversations happening simultaneously all across the universe. Okay, great. So let's take a break there. That went a lot quicker than I thought it would. So let's come back at 9:50. And then we're going to be talking about how to make our own HTTP requests using JavaScript.
And it's curl at all?
Not this time.